Okay, so in this example, we're going to look at a second problem where we use lhopital, but this was going to be one where we have to do a little bit of algebraic manipulation in order to be able to apply lhopital. So the example will be the limit as x approaches 0 from the right of x squared times the natural log of x. Now, let's do a little bit of sort of just thinking through this before we get into the nuts and bolts of it. So first off, note that we're approaching 0 from the right, and that makes sense because of this function right here, natural log of x. You cannot use negatives or even 0 for the input of natural log, so that we have to approach it from the right. But the important thing to note here is that we don't have the form that we really want. What we have is, as x approaches 0, this is going to be 0 times negative infinity. And that's not one of the forms. Remember that the two forms that we're allowed to have is 0 over 0 or plus minus infinity over plus minus infinity. And so we don't have that. But note, just a little algebraic trick, that if we rewrite this as the limit as x approaches 0 from the right of the natural log of x over 1 over x squared. Now note, these are algebraically the same because moving this into the denominator, you just have to get the reciprocal. And now I do have infinity over infinity. Technically negative infinity over infinity. So what we know is that both of these functions, again, we've manipulated this one to look like this, but these two functions are both headed towards infinity. And so again, L'Hopital's is going to help us answer, well, which one goes towards infinity the fastest? Now, note, if ln of x goes to infinity faster, so if the numerator heads towards negative infinity faster than 1 over x squared goes to infinity, then this whole thing is starting to blow up, and we will have a limit of infinity or negative infinity, and so we'll say the limit doesn't exist. On the other hand, if 1 over x squared heads towards infinity faster, then that means that the denominator is getting larger faster than the numerator, and the overall fraction should be going towards 0. And then finally, the third option is if they head towards infinity at some constant rate, technically some constant ratio. So in other words, maybe this one's always twice as fast as that one, or maybe this one's always twice as fast as that one, the numerator versus the denominator. Okay, so those are our three options. So if we look at the graph of the original function, x squared ln of x, that's this function right here, it appears that the limit is going to be 0. So notice as we approach 0 from the right, the limit appears to be approaching 0. Okay, now if we go back to this, that means we think, okay, if the whole thing is getting close to 0, that means we think that the denominator is faster, because if the denominator is faster, then the fraction's getting smaller. So we think that's the case. All right, so let's look at these as individual functions. So notice here, this here is natural log of x, and this one here is 1 over x squared. Now, if you note, at any given x value, it appears that this guy is larger than this one. And it's the difference is getting larger and larger and larger. In other words, 1 over x squared does appear to be going towards infinity faster than natural log of x is going towards negative infinity. So we think that the denominator is kind of ruling the
the play here, and therefore we think it should go towards 0. Okay, so again, what we did was we manipulated this function here to turn it into something that would be an indeterminate form that we could use. In this case, it's infinity over infinity. Okay, so um, let's apply L'Hopital's. So L'Hopital says that we can say, okay, we have the limit as x approaches 0 from the right of x squared natural log of x, which we're going to turn into the limit as x approaches 0 from the right of the natural log of x over x squared, 1 over x squared, sorry. And again, just as a little check, and I would appreciate seeing this in your work, show me that this is infinity, technically negative infinity over infinity. And so we can apply L'Hopital's rule. And so we can say equals the limit as x approaches 0 from the right. We're going to take the derivative of the top, 1 over x, derivative of the bottom. Now, we can think of this denominator here as x to the negative 2. And so its derivative would be negative 2x to the negative 3, which turns out to be negative 2 over x cubed. Now let's do a little simplification here. So we're going to have the limit as x approaches 0 from the right of 1 over x times x cubed over negative 2, which equals the limit as x approaches 0 from the right of, now note we can cancel out here and here, and so we wind up with x squared over a negative 2, and as x approaches 0, this is going to equal 0, just as we thought. So this confirms basically that when we put it in this form here, when we put it in that form right there, that the denominator is going towards infinity faster than the numerator is, and as a result, and not even like at a constant ratio, but rather it keeps getting larger and larger difference, so that the overall limit is 0.